And as we move forward with graphing trig functions, we're going to take a look at specifically the tangent and cotangent functions kind of together here. We've already discussed the ideas of sine and cosine graphs, and we've looked at different transformations of those graphs. We've looked at period changes, amplitude changes, phase shifts, and vertical shifts, and reflections as well. And so now we're going to take that information, just kind of our basic sine and cosine graphs, and use that to try to figure out what the graph of the tangent is first, and then we'll use that to figure out the graph of the cotangent. Okay, so a couple really important things to remember: that the tangent is the sine over the cosine. Those two expressions are equal. It's called an identity. We've seen that identity back, I think, in chapter 2. So that's shouldn't be new to us. The other thing is that the basic sine wave or sine function starts at the origin. I'm just taking one period and goes in the upward direction up to 1, back down to 0 at pi, down to -1 at 3 pi over 2, and then back up to the x-axis at 2 pi. The cosine function, instead of starting at the origin, starts up at 1 as its y-intercept, goes down immediately through the x-axis at pi over 2, down to -1 at pi, back up to the x-axis at 3 pi over 2, and then up to 1 at 2 pi. Okay, so those two graphs, we're going to keep those in mind because the tangent is the sine over the cosine, and so to figure out values for the graph of the tangent, we're going to use the ratio of the values from the sine and the cosine to get those. Okay. There's a few other points in here that we could use, but for now I'm just going to stick to these basic points here, or the 5 key points, I should say. One other thing that I want you to consider before we really get into this is that when you are dividing by a number, let's say you had a number like number 1 divided by something, 1 over a, and you were to divide that bottom number there was, say, getting bigger and bigger and bigger, okay? So let's say you were dividing by like 1 over 2, divided by 2. You get 1/2. If you're dividing by 10, 1/10, as the bottom gets bigger, you get 1/10, which is smaller than 1/2, right? If you were to divide by 1,000, you get 1/1000th, which is a very small number compared to 1/2 and 1/10. And so the bigger the denominator is, the larger the number you're dividing by, the smaller the overall fraction is going to be, okay? Or the closer to 0. So as a gets large, 1 over a gets closer to 0. Okay? And the opposite is true. Okay? So as the a value gets very small, if you're dividing by, if you're dividing by 0.5, 1 over 0.5 is 2. If you're dividing by, say, 0.1, 1 over 0.1 is 10. And the smaller the denominator gets, the bigger the number gets. Okay? So the opposite is also true. Okay, so that means as a gets smaller, 1 over a gets larger, essentially, farther from 0. Okay? Okay, so there's a couple key points here as we go. One other thing, probably said one other thing last time. One other thing to keep in mind is that if you divide by 0, the value is undefined, right? So 1 over 0 is undefined. And really, anything over 0 is undefined, okay? Except for 0, well, 0 over 0 is also undefined, for a different reason. Okay, so let's see. Let's take a look at this. Let's take a look at the sine over the cosine. So let's just start mapping out points. We'll start at 0, then pi over 2, then pi, and 3 pi over 2, and pi over 2, or 2 pi. And if we need some points in between, we can work with those. So starting at 0, I know that the sine, so let's say, actually let's do this. Let's do sort of a little xy table. And this is going to be for the tangent, okay? So let's start with an x value of 0. We know that the sine of 0 is 0. So sine is 0, so I'll put that on top. And the cosine is 1, I'll put that on the bottom. Well, that equals 0. So that tells us the tangent must have a point at 0, 0. Okay? Pi over 2, let's try that one for a moment. If we insert pi over 2, well, the tangent of pi, or I'm sorry, the sine of pi over 2 is 1. The cosine of pi over 2 is 0. And so you have a 1 over 0 situation, which we just mentioned is undefined. So that must mean that there's not actually a point on the graph at pi over 2. Just to represent that so that I don't mistakenly put a point there, I'm just going to draw a dashed vertical line through pi over 2. Okay, so now I know I can't draw any points on that vertical line. Because if I did, it would represent a point at pi over 2. We can't have that because pi over 2 gives us an undefined value for the tangent. Okay, let's look at pi now for a moment. Pi has a sine value of 0 and a cosine value of -1. So 0 over -1, of course, is still 0. So we have another x-intercept at pi. At 3 pi over 2, if we look at that, we're going to have -1 divided by 0. Which again is undefined. Okay. And so just like before, I'm going to go ahead and sketch in a vertical line there because I don't want to draw a point on that spot anywhere above or below 3 pi over 2. Okay, that would if I drew a point on that line somewhere, that would mean there is a defined value, and here there's no defined value, so we have to leave that blank. And then let's look at 2 pi for a moment. Well, at 2 pi you have the sine value of 0 and the cosine is at 1, 0 over 1, which is 0 also. Okay? All right, so that gives us, well, 3 points so far, and 2 spots where I know there will be no points. Unfortunately, I don't know anything else yet. I can't even get really a pattern here for the points. And so what I'm going to do is focus in on each of the quadrants. Notice that, or remember that, in each of these 4 intervals is one of the quadrants, right? The first quadrant, the angles in the first quadrant, second quadrant, third quadrant, fourth quadrant. And so if I were to just focus in on the ratios in those quadrants, I can get some more information about the graph. First of all, in this first quadrant here, from 0 to pi over 2, I'll put the 0 in there, from 0 to pi over 2, that's first quadrant, you have all positive numbers divided by positive numbers, right? Your sine and your cosine are both positive. All right, so from 0 to pi over 2, we know that we have positive divided by positive, which will be positive values. So that means the graph itself is going to be up in this upper region. I'm just going to put a little check mark here. We know the graph is going to be up here. Now, I don't know exactly where it's going to be, what kind of shape, what kind of curve, but it's all going to be contained above the x-axis because it's positive. So there's not going to be any graph, any part of the graph down in this lower region here, okay? Yeah, I'll just leave it at that. So the check mark means it's going to be there in that sort of infinitely tall rectangle almost. Okay, now in the second quadrant, from pi over 2 to pi, we know that the sine is positive, but the cosine is below the x-axis, making it negative. So we get positive over a negative, which is going to be negative. And that means the graph is going to be down in this lower region below the x-axis. Okay, so negative outputs for the tangent would be down below the x-axis. Similarly, if I go through the same sort of argument for the third quadrant, I'm not going to write all the details out, but third quadrant you have a negative over a negative, which would be positive. So in the third quadrant here, from pi to 3 pi over 2, your outputs will be positive because they're negative over negative. And in the fourth quadrant, from 3 pi over 2 to 2 pi, you have negative values over positive values. One's below the x-axis divided by one's above. And that will give you negative ratios there, okay? Check mark look better, there we go. Okay, so we know then that within each quadrant the graph's going to be up, then down, then up, then down, okay? We just need to then figure out what the shape of the graph is going to be. Well, to figure out the shape, I'm going to go ahead and fill in a few of the points in between here. With some values that hopefully we know. I'm going to start with a value of pi over 4, okay? If I can get this to right, there we go, pi over 4, right in between. It's halfway between 0 and pi over 2. Okay, so what I'm going to do next is redraw the x, y table. And I'm going to just real quickly sketch out our two special triangles because that's going to just help me to get these values a little bit quicker. So I've got the 45, 45, 90 triangle with 1, 1, and root 2 as the sides, and we've got our 30, 60, 90 triangle with 1, 2, and root 3 as the 3 sides. Okay, so that's going to help me out for just a moment. Let's go with the pi over 4. You know, it may not even use the 30, 60, 90. Either way, let's just focus in here. So with the pi over 4, that's a 45-degree angle. And when we look at the sine of pi over 4 is opposite over hypotenuse. That's 1 over root 2. Or we've called that root 2 over 2 when you rationalize the denominator. The cosine of pi over 4, or 45 degrees, is adjacent over hypotenuse, which is the same, 1 over root 2, or we've rewritten that as root 2 over 2. And when you have root 2 over 2 over root 2 over 2, same thing over itself, you end up with a value of 1, okay? So somewhere on the y-axis here is the number 1. And so right there, we'll put a value, or a point. And then, let's see, I guess at every other odd multiple of pi over 4, so here at 3 pi over 4, here's 5 pi over 4, and 7 pi over 4, then you're going to have a value similar because all of these odd pi over 4s are going to be angles on a 45-degree angle in one of the 4 quadrants, and they're all equal to either positive or negative 1, right? So you get that root 2 over 2 over root 2 over 2, but sometimes one's positive or the other one, and the other one's negative, and so forth. So what you're going to end up with is in the second quadrant here, you're going to have a positive sine and a negative cosine, so you get a negative 1. Let's sketch in where negative 1 would go, and then we'll put a point right there. And then at 5 pi over 4, they're both going to be negative, which will give you a positive ratio. And then at 7 pi over 4, they're both, the sine is negative, the cosine is positive. So again, one negative, one positive puts that point on the bottom. all right, in the negative side. All right, so that gives us 4 more points to work with. Okay, we could continue. Let's see if we take like a 30-degree angle here, just to see what happens. That's a pi over 6, which would be, it's in here between 0 and pi over 4, not halfway, but actually 2/3 of the way, but it's in there. And the output from that, the sine over the cosine, the sine of 30 degrees is 1/2. And the cosine of 30 degrees is √3/2. And what you end up with, the 2's will cancel. I'm going to skip all the work on this. You're going to end up with 1/√3 or √3/3, however you want to write that. Now that value of 1/√3 is actually going to be less than 1, right? Because square root of 3 is bigger than 1, so you have a bigger number on the bottom than you do on top. And so that number is going to be down here somewhere. It's not halfway, but it's down, it's below 1, so it's down in this region here, okay? I'm not trying to get real specific. We'll get, after the next point, I'll give you an idea what the curve looks like. If we do pi over 3 as our angle, which is 60 degrees, well, pi over 3 or 60 degrees, if you do the sine, it's √3/2, and the cosine is 1/2. And so you actually have the reciprocal of the previous value. Well, the reciprocal is the square root of 3/1. Well, here the bigger number is on top, smaller number is on the bottom, which means it's going to be above 1. So over here at pi over 6, the point's going to be above 1. And so what you'll find is that this curve, now I have it, it's not actually lining up. We don't want it to line up. This is going to be a curve. It sweeps up. And again, as the denominator, remember cosine's the denominator, as that number gets really, really tiny, close to 0, the fraction it represents is going to get really, really big. Okay, so that means as the x value gets close to pi over 2, the ratio is going to get very, very large. It's kind of shooting up in the air there, in the y direction. Now, again, it's never going to cross this vertical dashed line because there can't be a point there, right? If it crossed that line, then there would be a point on it, and it would no longer be undefined there. So it can't cross that line. It's got to just get closer to it. It keeps going up, but won't touch it. This is called a vertical asymptote. Okay, a vertical asymptote is a line that the graph approaches but never crosses. All right, so we have a vertical asymptote at pi over 2. Okay, again, that's a line that the graph approaches but never crosses. Okay, so you get closer and closer without crossing it. Now on the other side, if I were to plot this out, there is some symmetry to these graphs and the way that they map out. I'm not going to go through all the little details of all the points again. The main thing is to know that due to the symmetry in the graphs and the fact that the values are going to be negative, you're going to have another portion of the graph that just kind of shoots down toward that asymptote but never crosses it. Everything's going to be negative this time. Then on the right here, you're going to see another asymptote. I kind of drew it in with that in mind, but that's what's going to happen there. So there's also a vertical asymptote at, let me get rid of these triangles, 3 pi over 2. So there's a second one. And the graph will kind of repeat itself. So curving upward, and then over on the other side, it's going kind of down toward the asymptote. Okay. What I want you to see then is that this graph has a couple different wavelengths, sort of, or repetition within 0 to 2 pi, right? So you can kind of see, maybe one continuous swipe of this graph here between pi over 2 and 3 pi over 2. Or you could even see it this way as the distance, or the chunk from 0 to pi is the same as the chunk from pi to 2 pi, okay? So if I just take this chunk here, it's the same as this one. From 0 to pi and from pi to 2 pi are the same. And so essentially our period now, so we're going to consider this kind of a wave. It's not really the same sort of wave with a crest and a trough sort of idea, but it's still a cyclical pattern or a repeated pattern. And so the period of the tangent is represented by the length of that pattern, which is just pi this time, rather than 2 pi, which we had before. Okay, so the period of the tangent is pi, all right? Which is a little bit different. It's very important to note that. And it's also important to note that when we do period changes, remember the period changes come from having a factor, a numerical factor inside the tangent, so like tangent of 2x or something like that. When you have that value inside, then the period is going to be pi over that number, like pi over b. We had 2 pi over b for the sine and cosine. It's now going to be pi over b for the tangent. So it's a slightly different formula for the period, okay? So the period of y equals the tangent of bx is pi over b, okay? So it's a slightly different formula now instead of 2 pi over b, all right? Okay, so that gives us some more information. The point that is halfway between an x-intercept and an asymptote, in this case is the pi over 4, that's going to be at a value of 1. I'm going to call it the amplitude. Technically, it's not really an amplitude, because an amplitude would imply that there's a highest and a lowest, and you cut that distance in half. Here, there's no highest and lowest. This graph goes up indefinitely and down indefinitely. However, this halfway point is what we're going to use as sort of our amplitude. And so that value is going to be found in the same way that the amplitudes are found, by multiplying the tangent by something, right? So we had, if we have something like y equals a times the tangent of x, then the a, that multiplier, is going to be the number, I'm going to call it the amplitude, but it's the height of the graph halfway between the x-axis and the vertical asymptote. Okay, so it's very wordy, but I'm going to write it up here. A is the value halfway between the x-intercept and vertical asymptote. And of course, I'm abbreviating a couple of these things, the intercept and the asymptote. Okay, but you get the idea there. So a is the value. So if you have something other than 1 multiplying the tangent, that's how high this middle point is. Okay, so it just essentially stretches the graph out vertically again, or compresses it if that number is like 1/3 in front of the tangent. If it's 1/3 of the tangent, then that point would be pushed down or shrunk down toward the x-axis. Okay. Now, generally speaking, I've drawn this out from 0 to 2 pi, but oftentimes we're going to represent our 5 key points not using all of this information, because our period is pi, and the period has this this asymptote. If we went from 0 to pi, it has this asymptote right in the middle. What we're going to do instead is just kind of move the period that we're going to work with, and we're going to go, instead, we're going to plot this out on the left side. There is a mirror image on the left, and there's an asymptote at negative pi over 2, okay? So again, that's a mirror image. So this graph kind of reflects, it actually has what we call origin symmetry, which we've talked about before. It's an odd function. And so because the graph is nice and smooth around the y-axis here, we're actually going to use a period from negative pi over 2 to pi over 2 as our to give us our 5 key points. So it just makes the arithmetic a little bit easier. You can kind of center it at the origin and then add pi over 2 and subtract pi over 2, and then you can cut that in half, get your pi over 4 and your negative pi over 4 to get your 5 key points. So it's a little bit easier to do it that way than to just kind of move over to the right. So our period then is going to have x between negative pi over 2 and positive pi over 2, all right? After that, everything else is pretty much the same. You're still going to have your phase shifts, your horizontal shifts. You're still going to have your vertical shifts. They're going to be represented very similar in the tangent as they were with the sine and the cosine. So we'll go through a few examples in the next few videos so that you can see how all of those interact and how that plays out.